Yeah, okay, so my screen is visible.
Yes, sir.
Yes. Okay, yeah, yeah. Okay, so good evening and welcome to this week's tutorial. So, this is the tutorial for the content taught in the third week, which included the concepts of principal stress, principal planes, principal stress, planes where shear is maximum or minimum, like what values normal stress, normal traction takes on those planes, then more circle conditions for applying more circle and how to draw it and how to interpret it and use it. So again, as every week, we have a set of few curated questions which we'll go through together, and hopefully this will solve certain doubts. Okay, so the annotations are visible, right?
Yes, sir.
Yeah, okay. So the first problem asks which of the following is true with respect to principal planes of the stress tensor. So, as we learned, principal planes are the planes where your normal component, like the definition is, principal planes are those planes where the normal component of the traction is at an extreme. So, it's either maximized or minimized. So, okay, is this clear or do you have any other?
Sir, there is another thing which is between those also, no? Like which is neither not maximum and neither not minimum.
Yes, you are right. So, typically, if you look at extremes, we'll classify like a minima, a maxima, and a saddle point. So, I think you are referring to a saddle point, if I understand correctly.
Yes, sir.
So, yes, that is true. Uh, but principal planes are like defined in this way, like where your stress is either maximized or minimized. Normal component is at an extreme. So, is this clear or like this is a definition? This is this is the definition of a principal plane.
Yes, sir.
Okay. The next question asks the principal stress components are given by. So, does anyone want to answer this?
Eigenvalues of this stress tensor.
Yes, correct. So, if you look through the derivation of the principal components, you will typically have an objective function of the form mimi- which tries to sorry which tries to we typically have an objective function f of n comma lambda where lambda is a Lagrange multiplier which we apply to constraint equation which is summation ni equal to 1 minus 1 equal to 0 and summation sigma I j n j n I over I and j. So this is our objective function to obtain the principal planes. We set dou f by dou n k equal to 0, dou f by dou lambda equal to 0. And once we simplify this, we essentially obtain equation of the form sigma times n equal to lambda times n. So this is nothing but eigenvalue equation. So principal stress components which are given by lambda are essentially the eigenvalues. And the principal plane normals to the principal plane n are eigenvectors of this matrix sigma. which is nothing but the stress tensor. Third, okay, the third question on principal planes, which of the following statements is holds true? So, anyone wants to try this?
Traction vector acts along the plane normal.
Correct. So, as we just saw, it your equation for the principal plane's normal essentially reduces to an eigenvalue equation. But if you look at this is nothing but the traction T which acts on the plane n. So Tn is nothing but lambda times n. So your traction vector will always be directed along the plane normal n for principal plane. And since your traction, so if we draw it for like a body, if n is your normal vector, which is also your principal plane, then what this says is this is the direction of your Tn. So there are no perpendicular components here. So essentially your both shear components should vanish. Okay, so far?
Yes, sir.
Uh, okay, did anyone have a doubt? I didn't hear it. No? Okay, so I'm presuming this is clear. If not, you can voice your concerns now. Uh, okay, so we move to the fourth problem. The maximum magnitude of shear component of traction is given by.
Of the magnitude of the difference of any two principal stress components.
Okay, so this is you are so the answer is, so you are right when you are saying that the maximum magnitude of shear component should be, say, something like lambda 1 minus lambda 2 by 2. This is what you are saying, right?
Yes, sir. This
So
lambda 1, lambda 2 can be anything, I think. It's not necessarily the maximum. Then. Actually, we have three tau maxes, I think.
so if, say, if you have something like lambda 1 greater than lambda 2 greater than lambda 3, then you will have like three shear components arising. Say tau 1 2 is lambda 1 minus lambda 2 by 2. Tau 2 3 is lambda 2 minus lambda 3 by 2. And tau 1 3 is lambda 1 minus lambda 3 by 2. So these are the magnitudes that we get out of these three. If you have something like lambda 1 greater than lambda 2 greater than lambda 3, tau 1 3 will be the maximum. As you can see, you should get something like tau 1 3 is greater than both tau 1 2 and tau 2 3. So if you want like the maximum, I think the answer is this, like half the difference of the maximum and minimal principal stress components.
Yes, sir. Understood.
Yeah. Okay, so okay, the fifth problem. A point on the Morse circle which is at an angle theta. Okay, I think someone's joined. Okay, so the fifth problem. A point on the Morse circle. So I'll just draw a representative Morse circle. This is sigma xx plus sigma yy by 2. This point will be like sigma xx comma tau xy, and this point is sigma yy comma minus tau xy. Sorry, the label should be sigma and tau. Yeah, this is a representative Morse circle that I have drawn. And now they are asking a point on the Morse circle which is at an angle of theta clockwise from the point corresponding to the E1 plane. So theta clockwise. So this angle is theta. So this is the point P, and this is the initial point, say P1, and this is the final point P2. So we are told that P2 is at an angle theta clockwise from the point P1 which corresponds to the E1 plane. Okay, so in reality we know that if you move by say angle phi, if you change, if this is say E2 E1, and if you move your plane normal to a different location n which is at an angle phi with respect to E1, then on the Morse circle,
Two five.
you will move by 2 phi in the clockwise direction. So here we are given that our point on the Morse circle moves by say theta, so which means on
Theta
the
by 2 anti-clockwise.
yeah, theta by 2, it should move by theta by 2 in reality. So the plane will move at an angle of theta by 2 anti-clockwise from the E2 plane. Is this clear?
Yes, sir.
Okay. So the sixth problem is a simple true or false statement. All the principal components are always greater than sigma xx. Sigma xx represents the normal component of traction on the plane with normal along x-axis. So this
Sir, we cannot say that, no.
actually we can, I think we can. Suppose okay, suppose for the sake of argument that your z direction is nothing but say a principal axis. Then if we draw the Morse circle for this particular state of stress, you will end up with a point which is something like this, sigma xx and sigma yy comma minus tau xy. Now from the Morse circle we know that the points, and like from the definition of principal planes we know that the points where shear will go to zero, which are these 2 points, these are your principal principal stresses. So you'll have something like lambda 1 and lambda 2. So if you see, sigma x would almost always be greater than the minimum value of the principal stress component. So what this statement asks us is, if this is true, this is what we are asked. But if you look at, say, from Morse circle, you can quickly say that this will not always be the case. Like in fact, it seems like sigma xx will always be greater or equal to at least like the minimum of the principal stress component. So, oh, sorry. I think we are asked something like this. Sorry, my bad. We are asked this, but we are seeing this. Like we are saying the opposite to be true. Okay. Is is this clear, or do you want me to give another example?
Sir, in that circle, we have seen that my sigma xx is
Hmm.
less than some lambda 1, but it is greater than lambda 2.
Hmm.
So, in that sigma xx is less than all lambda 1, lambda 2, lambda 3 is wrong.
Yes, and that is what we are asked, right? We are asked if the principal components, all principal components, which means essentially we are asked if lambda 1 is greater than sigma xx, lambda 2 is greater than sigma xx, and lambda 3 is greater than sigma xx. But,
So, false.
exactly, but what this is what we are asked. But what we are saying is sigma xx will, in a sense, lie between, should be actually. I can write it that this is what is observed. So the given statement is obviously false. The seventh problem. Suppose we are given the radius of Morse circle. We are given R, radius of Morse circle. Does anyone remember what this R value is in terms of the components of stress?
Yeah, difference between those principal stress components by 2.
Okay,
Like,
so you are saying something like lambda 1 minus lambda 2 by 2,
yes.
provided lambda 1 greater than lambda 2. This is what you're saying, right? And if I want to write in these terms, sigma xx, sigma yy, and tau xy.
Uh,
Okay, so we'll have something like this. Sorry. Okay. Okay, so we'll have something like this. This is your R. This is sigma xx comma tau xy. This is sigma yy comma minus tau xy. And we know that the center is sigma xx plus sigma yy by 2, and these end values are lambda 1 and lambda 2. So your R from Pythagoras theorem becomes sigma xx minus of sigma xx plus sigma yy by 2 whole square plus tau xy whole square, which is nothing but sigma xx minus sigma yy by 2 whole square plus tau xy whole square. So this is your R in terms of the stress components, and this is in terms of the principal stress components. So this is the only piece of information that we are given, and we are asked what we can find. So can we find the principal stress components? Can we find lambda 1, lambda 2?
no, we will
Correct.
find relation. We will find.
Yes, we have a constraint on lambda 1 and lambda 2. We don't necessarily know what their actual values are. So if say R is 2, lambda 1 lambda 1 can be 4, lambda 2 can be 0, lambda 1 can be 8, lambda 2 can be 4. And we can have like infinite number of these relations. Can we find the maximum shear component of traction?
Sir
So
is nothing but Arna, sir. So we can't
yes, so this is the maximum shear component, which is nothing but R. So this we can't, this we can. Can we find the magnitude of total traction on any plane? So like if we want to look at X plane, can we find like the traction on X would be something like, can we find the total magnitude? Sorry, double arrows.
Sir, it's sigma xx, sigma y are given.
Hmm. So we are given only R, right? So we can't find this. R is this value, not this. So this is also not there. And can we find the difference of normal components of traction on E1 and E2 planes? So this essentially says, can we find like sigma xx minus sigma yy if we are given R, if we are given these? So no, that is also no, right? So this is our answer. So we can only find the maximum shear component if R is given out of these four options. Okay, the eighth problem. We are looking at a point inside a fluid body. So if you remember, for a fluid body, which is the traction for a fluid body under rest is nothing but minus P times N, where P is the pressure, and sigma is nothing but minus P times I, which is the identity tensor. So we know this, and we are asked every plane is a principal plane. So is this true?
Yes.
Yes. So if we choose any coordinate system and write down sigma in its matrix form, we'll end up with this matrix always. So as you can see, only the normal components are here, no shear component. So it's any plane you choose is essentially a principal plane. Second is all principal stress components are equal.
Yes.
Again, yeah. So principal stress components are the eigenvalues of this matrix, and if you want to calculate the eigenvalues, we'll solve this equation. And once we do that, we'll see that eigenvalues are all equal to minus p. So this equation is essentially written as 0 minus p minus lambda, 0 0 minus p minus lambda. Determinant is 0, which gives us minus p minus lambda whole cube equal to 0, which gives us all three eigenvalues equal to minus p. And the third question is Morse circle reduces to a point. So in Morse circle, the radius would be mod of lambda 1 minus lambda 2 by 2. But since lambda 1 and lambda 2 are both equal to minus p, you essentially end up with 0 radius. So your Morse circle with a radius r has essentially shrunk down to a single point. Okay, so all three statements are true. Yeah. Uh, this is clear, right? It's a relatively straightforward problem, I think. Okay. Yeah. So the ninth problem: if at a point we choose a coordinate system such that none of the coordinate axes is aligned along the principal plane's normal. So suppose we have n1, n2, and n3. These n1, n2, n3 are essentially principal planes normal. And we are told that we choose a coordinate system so that none of our chosen axis is aligned along the principal planes normal. So we can choose something like E1, E2, and E3. This is the coordinate system that we choose. Then which of the following holds? Uh,
We cannot apply the concept of mode circle to the test.
yes, correct. So as if you remember, Morse circle, the concept of Morse circle is applicable only when the concept of Morse circle is applicable only when at least one of our E1, E2, or E3. So at least one of E1, E2, E3 lies along one of N1, N2, and N3. So this condition must hold true. This condition needs to be true to apply Morse circle. Okay, so this comes directly from the way we derive the Morse circle. Okay, and finally the 10th problem. Suppose we choose a coordinate system such that one of the axes is normal to one of the principal planes and draw the Morse circle. So, so we are initially choosing a coordinate system. Suppose this is n1, n2, and n3. Ni are principal plane normals. Initially, we are choosing one of the axes is normal to one of the principal planes. So one of the axis is say E1, which is aligned along a principal plane normal, and the other two may not be. So you have say E2 and E3. This is what we chose, and we are drawing a Morse circle for this problem. You have got sigma, you have got your tau, and your values will be r. The radius will be say r equal to mod of lambda 2 minus lambda 3 by 2. Now, so where this part is done. So now we choose another coordinate system such that one of the coordinate axis is aligned along a different principal planes normal and draw the Morse circle. So instead of E1 being aligned to N1, we can say align E2 along N2. We can align E2 along N2 and then move around E1 E2 along N2 and move around E1 and E3. So this is for this. For this one, we'll get a Mohr circle between say lambda 1 and lambda 3 and this state of stress. Your R13 would be equal to lambda 1 minus lambda 3 by 2. Now, which of the following statements is true? The radius of the two Mohr circle must be the same. So, the first one asks if R13 is equal to R23. So, as you can see, as you can see, it's not necessary. So, this statement doesn't necessarily hold true. The radius of the two Mohr circle can be different. So, as like the first two options are mutually exclusive, so either they must be equal or must be same or can be different. So second one holds. The third one asks if the center of the two most circle is same. So if we see C23, it will be say lambda 2 plus lambda 3 by 2 comma 0, and C13 would be lambda 1 plus lambda 3 by 2 comma 0. As you can see, it's not necessary that C13 and C23 are always the same. So only option B, which is the radius of the two Mohr circle, can be different. This is clear, or do you want me to explain it again? Did you guys understand this?
Yes, sir.
Okay, so that concludes this week's set of problems. Do you have any conceptual doubts that arose when going through week three's lecture?
Sir,
Hmm.
is there any chance of finding normal stress and shear stress for a planes whose normal is not perpendicular to those three principal planes?
Okay, sorry. Can you repeat your doubt once again?
Is there any way to find normal stress and shear stress for a planes whose
Hmm.
normal is not perpendicular to any of those three principal planes?
Yeah. So you are saying that if we have say x, y, and z, so you want to find at say this n, right? Is that is this what you are asking?
Yes, sir. But that normal is not perpendicular to any of the three principal planes.
So ex, ey, and ez, these are so none of these is equal to n1, n2, n3. This is what you are asking, right?
Yes, sir.
Okay, so this is your point P. So if we look at the stress tensor at point P, it will be sigma xx, tau yx, tau zx, sigma x, sigma x, sigma xy, sorry, tau xy, sigma yy, tau zy, tau xz, tau yz, and sigma yy. So if the state of stress, which is the stress tensor, if it is known at any given point P, and we want to find the traction P on a given on a given plane with normal n, then we'll simply do this, right? P is equal to sigma times n. So that should get you the traction. And if you want, say, the normal component, we'll write down sigma n is Tn dot n. If I simplify this essentially is sigma ij nj summed over j. And if I simplify this, this is sigma 1j nj sigma 2j nj sigma 3j nj dot n1 n2 n3, which if you write can be written as summation over j sigma ij nj times ni. So this is your like normal component of the traction, and similarly you can calculate tau n perpendicular as Tn minus sigma n and n, which is Tn minus Tn dot n into n. So if you know the state of stress, and if you want to calculate, you can first go about calculating traction Tn for the given plane n. Using that, you can do a simple dot product of the traction. So this is your n, this is your Tn, and if we split it, this is your sigma nn, and this is your tau n perpendicular.
Yes.
So
Yes, sir. Understood.
you got this right. Sigma nn is this and tau n is this. Okay, so if you remember, this was derived in, I think, the very first lecture. Yeah, the very first lecture. We take like a small triangle about a point, and then we tetrahedral about a point P, and we slowly shrink down the tetrahedron to obtain what traction we'll get on this particular plane given by n as a function of tractions on three mutually perpendicular planes. So like T1, T2 and T3. E1 perpendicular to E2, which in turn are both perpendicular to E3. Okay, so anyone else has a doubt? Okay, I hope you guys are able to follow the video lectures and whatever is being taught there. Also, how are you finding the assignments? Are you able to handle them, or are you finding them tough?
Yes, sir. We can handle that.
You can handle them, right? Okay. So, yeah, if we don't have any doubts, then this is it for today. Do keep learning, keep solving the assignments. Yeah, turn up to these sessions. I'll try to address your doubts to the best of my abilities. And yeah, happy learning.